Okay, good morning, everyone. I'm Chen Yang from Wuhan University. Today, my talk is about how to perform data analysis for recommendation system. So first of all, we all go over about how a recommendation system works. Specifically, all solutions so far come on user behavior. This is reasonable since we can only know you better if you after you show us more preference, right? So, for example, we can identify similar users based on the purchase patterns, or to identify the similar items based on the common users that consume the same item pair. So, however, right now we have up to billions of items and millions of users in many platforms. So for a single person, the number of behavior for a user is very limited, say hundreds of interactions per year. So the data sparsity problem has been a long-standing issue for recommendation system, and many efforts have been devoted to alleviate this problem. For example, by exploring auxiliary information like textual review, knowledge graph, or user and item profiles. So under such a deep sparsity situation, the common element is to fit all available user interactions into a model. Here we list the two examples in the up figure. We can see that all historical items are taken into consideration for sequential recommendation. Also, in the bottom figure, the same thing happens for the next basket recommendation. So for the first example, it is obvious that there are two interests for this user. One is about entertainment, the other is about sports. So for a given candidate item, just some of we can see some of the history items are relevant for happy hours, identify the user's preference, where the rest interactions are irrelevant, or even what's stories. Also, the same situation appears for next basket recommendation. This is because the user's behavior are uncentered and to some degrees, mainly because we have diverse interests from time to time. So similarly, when we exploit auxiliary information to enrich the context, not all of the set information are useful. Some of them may harm the precise preference learning or complicate the model training to be less effective. One existing solution is to utilize attention mechanism such that useless signals will have less weights. However, based on our experiment analysis, the small weights can accumulate to a larger number, given many of the items or signals could be considered as noise. So one simple idea comes out, I guess, from all of you, right? So which is also intuitive. Instead of using attention mechanism for importance weighting, we can choose to simply remove the useless features. That is using only the relevant information which is set to the target. However, this simple idea faces many difficulties since it is infeasible to ask a user about which previous items affect the current behavior, or making breakers result store, right? But the things are not worse since there are some parameters can help achieve the purpose. One possible way is to is to call for other training. We can formulate the Denoising task as a reinforcement learning problem. We can optimize the Denoising decisions by improving the recommendation performance, which is also a final task. Also, we can devise some weak or self-supervised objective in terms of data Denoising. Say, a contrastive learning, which helps the model traverse to a better point. Okay, the first attempt for us is for next basket recommendation. This task is to identify what items.
I'll just give you the microphone, otherwise the people on Zoom can hear us. I know it's a small room and you can speak with that microphone.
Okay, thank you. So the first attempt for us is for next basket recommendation. This task is to identify what items will be purchased in the next basket, give a sequence of purchased baskets. One simple way to perform denoising is to remove some irrelevant items from this historical basket, with respect to the candidate item. Here we utilize this is the architecture or workflow of our proposed solution. We utilize a MLP network to identify relevance of each item in the history basket by taking the item as well as the candidate item as input. So to implement the hard coding scheme but enable differentiable, we choose to utilize Gumball softmax to mimic the battery selection. After that, we can retain the relevant items in each basket and form a new qualitative basket sequence. In the same way, we also get irrelevant item basket sequence, right? Or we call qualitative basket sequence. So for each kind of basket sequence, we can represent each basket by arrange the item embeddings inside it. Then a GIU module is utilized to encode the whole sequence. Now recall that we can not have any ground truth about the item relevance from the user. Remember? So, but we found that we can have such three types of basket sequence: the qualitative one, the top one, and the original, and the native basket sequence in the bottom, and the original basket sequence there, where each basket contains all the corresponding items. With these three sequence, logically, we believe the qualitative basket sequence should have really a higher score than the ground truth. For the ground truth, than with original sequence. Also, the original sequence can help us generate a higher score instead when using the native basket sequence. That is to say, we can form a contrastive learning objective in this sense, without any supervision from about the relevance, item relevance. So we evaluated the proposed solution over 4 real-world datasets. The performance metrics include recall, procedure, F1, and NDCG. So the results show that this simple idea works significantly to improve the recommendation performance to some extent. And we also dive deep into the different user groups in terms of the average basket size. So we can see that a larger performance scale is observed for the users that have a bigger basket size. It means that for the scenario with monorace or what can help more. After that, we further investigate the possibility of perform denoising for better sequential recommendation by using reinforcement learning. Actually, we formulate the item level denoising as a macro decision process along the sequence. This is the whole architecture of our solution. Actually given a target item, we iteratively figure out whether to keep it the current history item or not. After that, we can also form two subsequences, the positive one and the negative one. So, for example, the positive item sequence contain all relevant items identified by our policy. For the purpose of denoising or the decision making through the policy network, we further utilize existing algorithm to mine frequent sequence patterns. These sequential patterns up to 5 orders are encoded and used to get the denoising decision making. So as to the reward designer, we still believe the positive sequence can generate higher score than the negative sequence. And then we take the margin between these two scores as the reward. We conduct experiments over 4 real-world datasets for sequential recommendation, and the metrics include the hit ratio and the NDCG. So here you can see the results that the denoising can deliver a significant performance gain over the baseline methods. We also perform a case study by comparing our proposed solution against a available attention-based model, BERT for rank. Here we can see that using attention mechanism in BERT for rank can give higher weights to the relevant historical items towards the target item. But our proposed denoising solution can just kick off these irrelevant ones. Means the items identified by BERT for rank with less weights. So this can actually kick off these irrelevant ones can ease the model training process and lead to better discriminative ability. Okay. Also, I just mentioned that auxiliary knowledge is widely used to address the data sparsity problem. It is also useful to perform data denoising in a context-aware fashion, such that only relevant set information can be leveraged for preference estimation. So hence we take the news recommendation with knowledge graph as an example. So in this figure, we can see that for an entity named Carrie Spacey, the knowledge graph could contain semantic relations to every aspect of this person, covering both his career and the political view. However, the relevant knowledge towards the user 1 and the user 2 are quite different. It is obvious to see that the interest of user 1 is more about entertainment, and where the user 2 focus more on the political issues. Hence, we need to do some selection when using the auxiliary knowledge in different contexts. First, we extract the entity mentioned in the title of each news article, and this entity is called a seed entity. Then, initial interest graph is formed by collecting these seed entities following the timeline. And for each of these seed entity, we can search the knowledge graph and pick the relevant labels to enrich the whole context and lead to better user understanding. The whole process consists of 3 steps. For step 1, we add loads from the noise graph. Then we propose a recurrent graph convolution to obtain the interest embedding at the current time. Then some nodes from noise graph are just removed. Then we continue this process until we reach the end of the news sequence. This is the first work that perform data denoising over the noise graph for news recommendation. And there are larger scale benchmarks. Two larger scale benchmarks are available. One is MITE, and the other is Advisor. They are from 2 different languages. So we compare the corresponding knowledge graph for DBpedia by ourselves. These knowledge graphs are shared publicly for us. You can see that there are 1 million users in MITE and more than 3 million users for Advisor. The results show that the proposed solution can achieve much better recommendation performance than a series of existing models. So then we switch our focus on micro radio recommendation, but still try to grab the benefit of data denoising. Nowadays, there are a tremendous number of micro radio uploaded every day. For example, TikTok and Kuaishou, which is also a leading radio sharing platform in China. We all know that a micro radio could cover more thematic information than other medias. However, it is very expensive to extract visual content due to the larger scale nature of these platforms. Also, we found that the user feedbacks are very sparse as well as noisy, or even more noisy than the other UGC platforms. The vast majority of user actions are still just sweeping, up to the next radio, so leaving very sparse user feedbacks. Without explicit user interaction, it is very hard to tell whether the user really likes what he or her or he watches. So, also, we can utilize watching time. Also, we can utilize the watching time to speculate the user's preference. It is their noise. Plus, the average life cycle of a micro radio is extremely short, maybe less than 22 hours, most of them less than 22 hours. So it makes our data more sparse. So we choose to build a marriage between textual information and the graph neural network to support the radio content understanding and user preference learning. We resort to extracting concepts mentioned in the capture and commands. Then a heterogeneous tripartite graph is then constructed by collecting users with video nodes and video nodes with associated concept nodes. We first apply convolution by propagating a semantic concepts information to the related micro radio and the users through the aggregated order concept to items to micro radio and the radio and to user. So we call this process warm up. With the user and the item representation calculated by the warm up phase, graph denoising stage aims to extract a subgraph from the for a given user. So that's the noise micro radio concept just removed in a breadth first search fashion. Then we again perform the same convolution as in the warm-up stage. That is to say, after we get the new structure, we perform from the right to left again to derive the user representation. Then this refined user representation is used to calculate the ranking score in terms of inner products. The extensive experiments over a larger scale Quasar micro radio dataset and traditional e-commercial benchmarks from different languages are conducted. Our proposed solution achieves significant superior recommendation performance to the existing state-of-the-art technical alternatives. We also observe that the larger performance gain is obtained over the long-tail items from Quasar dataset. So, and last, allow me to highlight some key takeaways here. So in this talk, we show that denoising is promising for many recommendation taskers, and it ensures more noiseless data and easy the model training process. Also, given the missing of the relevance separation, we can use contrastive learning, auxiliary signals, and end-to-end reinforcement learning to implement the data denoising. And last, this is a typical architectural designer following the principle of minimalistas. So more is less and less is more. It here works for everything. Here is our relevant publications, and thanks again for your attention. Okay.